Good afternoon and welcome back. Now we move further for the next presentation on RCC dam design by Dr. Quentin Shah. May I request my colleague to play the recorded presentation, please?
Ladies and gentlemen. My name is Quentin Shaw, and as part of the InCold virtual workshop on applicability and feasibility of roller compacted concrete dams, this afternoon I'm going to be presenting to you on the subject of RCC dam design. So I will start the presentation with an introduction and go on to talk about different types of RCC and different RCC dam types. I'll then talk about the critical properties for different RCC.
There is no sound. Can you please restart the presentation?
Good afternoon, ladies and gentlemen. My name is Quentin Shaw, and as part of the InCold virtual workshop on applicability and feasibility of roller compacted concrete dams, this afternoon I'm going to be presenting to you on the subject of RCC dam design. So I will start the presentation with an introduction and go on to talk about different types of RCC.
मेरा ठीक है, तेरा वाला तो मैं देखा था यार, उसमें पेड़ है एक को गंदा सा।
Good afternoon, ladies and gentlemen. My name is Quentin Shaw, and as part of the InCold virtual workshop on applicability and feasibility of roller compacted concrete dams, this afternoon I'm going to be presenting to you on the subject of RCC dam design. So I will start the presentation with an introduction and go on to talk about different types of RCC and different RCC dam types. Good afternoon, ladies and gentlemen. My name is Quentin Shaw, and as part of the InCold virtual workshop on applicability and feasibility of roller compacted concrete dams, this afternoon I'm going to be presenting to you on the subject of RCC dam design. So I will start the presentation with an introduction and go on to talk about different types of RCC and different RCC dam types. I'll then talk about the critical properties for different RCC dam types and then move on to talk about the very important subject of thermomechanical analysis of RCC dams. And I'll expand this theme to talk about stress relaxation creep, thermal effects, and temperature load issues for RCC dams, looking at the critical impacts of low stress relaxation creep in arch dams and the impacts of stress relaxation creep in gravity dams. I'll then look at developing this concept to then describe and underline the correct approach for stress relaxation creep stroke thermomechanical analysis of RCC dams. We'll then change the theme a little bit and look at the important differences between RCC and conventional mass concrete dam design. And to extend the subject that I introduced earlier, I'll look at differing RCC requirements for different RCC dam types. Then go on to talk about facing systems for RCC dams, the different options. I'll look at describing in principle RCC arch dams, and then I'll sort of bring everything together and present a summary of the success factors in RCC dam design and a general summary of the full presentation in its entirety. An RCC dam is a type of concrete dam which requires more detailed consideration of materials and construction procedures than is the case for a conventional mass concrete dam. And it also requires a consideration of additional issues and parameters in the process of design. So RCC dams were first built as a complete dam in the early 1980s, and by 2021 more than 900 major RCC dams were in existence worldwide, of which 83 are arch dams, so that's a little less than 10%. And of these 83, 72 are in China and 11 in the rest of the world, which includes South Africa, Panama, Puerto Rico, Laos, Pakistan, Algeria, Lebanon, Honduras, and Turkey. In terms of the state of the art, of RCC, it's now possible to construct a range of dam types in roller compacted concrete, from the low stress hard fill gravity structures, where one might typically be working with a concrete with a compressive strength of the order of 2 to 4 MPa, although usually in fact higher, all the way through to arch gravity and even thin arch dams, where the compressive strength of the concrete can quite easily be as high as 40 megapascals. And while it is true to say that RCC technology has probably reached a certain level of maturity, it's equally true to say that the technological development in RCC remains ongoing. And while this series of presentations as part of this training workshop relate primarily to Bulletin 177, there is certain aspects, particularly of this design presentation, that relate to developments since Bulletin 177. So in this regard, the key areas of development in RCC include a new understanding of the early stress relaxation creep behavior of different RCC types, a better understanding of the requirements of RCC mixes and RCC mix design, and a better understanding of the requirements of RCC dam construction, specifically with respect to creating bond between placement layers. So whereas it is true to say that the concrete strength and zoning may differ for conventional mass concrete dams of different height and for different loading conditions, the primary configuration of the structure and the method of construction remains the same. This, on the other hand, is not the case for RCC, for which quite different concrete characteristics can be created, which imply different structural forms and even different construction requirements and approaches. So as will be repeated many times in this series of presentations, simplicity is the key element in a successful RCC dam, and this is primarily related to the application of horizontal construction. Consequently, the design of an RCC dam cannot really be discussed without addressing the construction and the applicable mix type and design. Now, this presentation specifically focuses on RCC dam design and attempts to minimize the inevitable spillover or overlap into RCC mix design and construction, although you cannot really talk about any one of these subjects without realistically addressing and including the impacts of the others. So with RCC types of different composition and strength, different structural dam types are applicable. So starting at the bottom end, the lowest cementitious materials end, for symmetrical section hard fill or CSG dams, or as they're now called cemented materials dams, a very low cementitious material content can be used, as low as 60 kilograms a cubic meter. And realistically, this is the sort of material that was the origin of roller compacted concrete dams, and the hard fill, symmetrical hard fill configuration was at that very origin as well. And realistically, this was a hearting material with very low strength requirements. And a zero bond between the placement layers is a critical factor of this type of roller compacted concrete. And impermeability must be created by a separate element on the upstream face. Now, this mix type will give a zero vertical tensile strength, and consequently the dam type is not realistically suited to regions subject to high seismicity. The next step on the cementitious materials scale is low cementitious RCC, or LCRCC, which is an RCC containing less than 100 kilograms per cubic meter total cementitious materials. And mixes of this type can typically take two forms. A more modern variant will indicate a very high non-cementitious fines content with a total paste content of between 210 and 240 liters per cubic meter. And in this regard, it's particularly important to understand the differentiation between cementitious paste and total paste. And in modern RCC dams, total paste is the critical element. And if cementitious paste involves cementitious materials, water, admixtures, and air, total paste is the cementitious paste plus the non-cementitious fines that come from either crusher sand or manufactured dust, milled rock. On the other hand, there's a more old-fashioned variant of LCRCC, which will involve simply designing the RCC mix for the necessary target strength, adequate workability, and adequate density. So while the former RCC type will produce a workable and cohesive mix with the right design, which can be made impermeable with bedding mortar between the layers in the zone of the upstream face. The latter will typically produce a mix that segregates during construction and will require a separate upstream membrane or element for impermeability. So in all cases of LCRCC, a broader dam section and a lower stressed structure is required. And next we come to medium cementitious RCC, MCRCC, which is a mix containing between 100 and 150 kilograms per cubic meter of total cementitious materials. And this can also take two forms. A modern variant will use non-cementitious fines to enhance the total paste content to somewhere in the region of 100 liters, 180 liters per cubic meter, more than, with levels that this low level of paste requiring a prescriptive aggregate specification. And then you have the more old-fashioned variant again, which involves designing the RCC mix for the necessary strength, adequate workability, and adequate density. So now, due to the improved understanding of RCC mix requirements, the use of the former mix type is increasing and the latter type is decreasing, with the former producing workable, impermeable RCC. However, a limitation of this RCC type is that it will not realistically allow high levels of interlayer bond. Sort of tensile strengths are not really much more than 1 MPa and cohesions not more than 1.25 MPa. And consequently, this RCC type is best suited to lower stressed gravity dam configurations. Then at the top of the scale, we have high cementitious RCC, HCRCC, which is a mix containing more than 150 kilograms per cubic meter total cementitious materials. And these mixes typically take a single form, a high workability, cohesive mix with total paste content greater than 180 liters per cubic meter, and often using a prescriptive aggregate specification. Without that specification, the total paste requirements are somewhat higher. And usually a set retarding admixture will be used to extend the initial setting time of this type of RCC to approximately 24 hours. And the concrete is then described as a super retarded high workability RCC. This approach allows a maximization of hot joints, which maximizes interlayer bond. And even so, a design limitation exists in a maximum sustainable vertical tensile strength of the order of 1.5 MPa, which can be compared to a number of over 4 MPa for a conventional mass concrete. Nevertheless, this type of RCC is suited to higher stress structures, including arch dams, but also offers constructability benefits. So in some instances, this RCC type is selected because of its constructability advantages and because of its good bonding between placement layers. And if we look at the critical properties of the different RCC for different RCC dam types, the first critical property or the overall property is the bond between the layers, and this in the form of tensile strength, shear strength, particularly joint cohesion, and permeability. So this really defines our bond between the successive placement layers. And when we're talking about the typical properties that can be realized for each of the RCC types that define the criteria for the design of the different RCC dam types, we can look at these following properties, although we have to say that it's always necessary to verify these properties through testing. So what I'm going to give you here are just typical ranges of applicable properties. So when we're looking at hard fill, at the low cementitious end of the spectrum, realistically a tensile strength between layers of 0, a shear strength depending on the nature of the aggregates particularly, of between 37 and 50 degrees, and realistically a cohesion of 0. Permeability, you have to expect permeability along the joints between layers in a hard fill type of structure. So with lower cementitious RCC, we have a situation with tensile strengths typically assumed as 0 where no bedding is used, and maybe as much as 0.5 MPa at the top end when bedding might be used. Shear strengths will typically be between 37, friction angles of between 37 and 50 degrees, and cohesions between layers would not realistically be more than 1 MPa, and that number could be as low as 0 when debonding between layers is observed. This will give you a permeable RCC matrix unless bedding is included between the placement layers, in which case impermeability can be created. The medium cementitious RCC, tensile strengths between typically 0.3 and 1 MPa, depending on the mix approach and the use of bedding between layers. Shear strengths for this with friction angles of the order of 40 to 50 degrees, and cohesions limited to perhaps 1.25 MPa. On the old type of this type of mix, you'd be looking at partly permeable, and realistically you wouldn't be able to be certain of impermeability without a bedding layer between the placement layers, but a modern mix can be designed in this type of RCC for impermeability. The top end, the high cementitious RCC, tensile strength, as mentioned, realistically a maximum of 1.5 MPa, and this will depend again on the mix type, the amount of paste, etc., and the use or the use of bedding. Shear strengths typically between 40 and 50 and even more friction angle, and cohesion of more than 2 MPa. And this type of RCC will be designed generally for impermeability. Now, a particular issue that has some relevance to our RCC dam design is guidelines that have been written into the ANCOL 2013 guideline on the design criteria for gravity dams. And while these aren't necessarily applicable anywhere outside Australia, it's extremely interesting to see that a fraternity of dam engineers have placed these requirements and constraints on particularly low cementitious RCC. And these state that unless there is a strong evidence to support bonded lift joints or investigations based on cord samples are undertaken, all concrete lift joints should be considered as unbonded. And for an unbonded joint, residual shear strength properties should be considered. Furthermore, the shear strength properties to be used should be exceeded by 80% of all test results. So these requirements imply the need for a very significantly heavier section in the case of a lower cementitious RCC dam, where a majority of unbonded lift joints can realistically be expected. So this has a big impact because a lot of RCC dams will not have been designed with this principle as a thinking. So moving on to talk about a very important subject of thermomechanical analysis of RCC dams. thermal expansion at a low concrete elastic modulus, and later thermal cooling at a higher concrete modulus, with basically the difference creating a shrinkage of that concrete. But this approach actually resulted in a misinterpretation of the actual behavior of the concrete. And stress relaxation creep that occurs during the hydration cycle was assumed to be a function of the concrete nature of the concrete and the hydration temperature rise. And this was applicable essentially for all approaches used for the thermomechanical analysis of all concrete dams, essentially. And in fact, it's been demonstrated that stress relaxation creep is a stress-dependent function. So it's not just dependent on the nature of the concrete, and it will change, it will be different with different natures of concrete, as in conventional concrete, roller compacted concrete, and roller compacted concrete with different cementitious materials compositions and contents. It will vary with that, but it's not so much the hydration temperature rise that influences the extent of stress relaxation creep, but rather the extent of restrained thermal expansion. So stress relaxation creep during that hydration process is actually a stress-dependent function. It's not a temperature-dependent function. It's about thermal expansion and how much that thermal expansion is actually restrained from actually occurring. So looking now at stress relaxation creep, thermal effects, and temperature loads, research and analysis on a number of RCC dams, including, importantly, 2 arch dams, revealed very different levels of stress relaxation creep in different RCC types. From an effective 0 stress relaxation creep on 2 arch dams, and notice the point effective 0, I'll explain that later. So from 0 on 2 arch dams to well in excess of 100 microstrain in the case of lower workability, low cementitious RCC. And this is particularly relevant in this case because this RCC might have had an adiabatic hydration temperature rise of the order of 7 to 8 degrees. So in fact, even more than the temperature equivalent of the hydration temperature rise was seen in the stress relaxation creep in this particular low strength RCC type. Additionally, very low stress relaxation creep was demonstrated to increase surface gradient at cracking. Now this implies that the generic approach that was developed, such as maximum gradient, thermal gradients of 20 degrees between internal and external zones, that was developed for a conventional mass concrete on the basis of the typical performance of conventional mass concrete. What we're seeing in RCC is different in low stress relaxation creep RCC, and consequently a greater sensitivity to these gradients exists. However, unlike RCC, when a crack occurs in the surface of an RCC dam, that crack doesn't tend to propagate upwards. In conventional concrete, it does. It's very difficult to stop that crack. In fact, in the case of RCC, placing a warm RCC on top of that crack typically seals it again, and the problem of propagating cracks doesn't occur. Particularly low stress relaxation creep was established in fly ash rich, high workability RCC, to the extent that expansion during construction was actually measured at Changarona 1 dam. So the graphics shown here were measured at strain gauges across the joints at an elevation approximately 10 meters below the crest level, a little bit more, and on the upstream side, so several meters from the upstream face. What was established was that for the placement above those gauges, a linear expansion on those gauges was determined, which occurred until the horizontal construction was completed. So in other words, at the level of the spillway crest, it stopped and just stopped and disappeared. So for the continuous horizontal construction above for the non-overspill crest, etc., there was no such, none of this expansion. It only occurred as concrete was placed fully from abutment to abutment horizontally. It happened linearly and stopped. And to the extent on those gauges of indicating an expansion on the upstream side of the order of 72 microstrain. And back analysis demonstrated the effective zero stress relaxation creep that was seen in these arch dams is actually a consequence of, first of all, very low stress relaxation creep and this pre-compression effect with the actual arch crest getting longer. So it's a combination of these two things, low stress relaxation creep and this pre-compression of the crest getting longer as it's being built. And in fact, that only happens because of the low stress relaxation creep. So as the structure becomes more flexible with height, its containment of the thermal expansion is less, and therefore it is actually physically able to expand. So that, because of the low stress relaxation creep, so you get this combination of two things that give us this overall effect of zero stress relaxation creep. So what is stress relaxation creep? Well, let's start looking at this with our typical temperature time curve for concrete in the core of a dam structure. So we have our T1, which is the placement temperature, T2, the maximum temperature during hydration, T3, which is the zero stress temperature, and T4, which is the final coldest temperature during an equilibrium cycle after all the hydration heat has been dissipated. So the tricky one here is our T3. And T3, basically at T1, the concrete is not under any stress. It tries to expand, it experiences compression, goes up to T2, and when it comes out of that compression again and is at zero stress, that's our T3 temperature. And T3 is then essentially equal to T1 plus the temperature equivalent of the stress relaxation creep. So that difference between T1 and T3 is the shrinkage of the shrinkage of the concrete caused by stress relaxation creep. And when I say, so RCRC, stress relaxation creep strain can be translated to an equivalent thermal load. So we have a temperature equivalence or a strain equivalence of that stress relaxation creep. Then let's look at more detail at stress relaxation creep. So as cementitious materials hydrate, the product of the reaction is smaller in volume than the constituent components. So the product of the hydration gel is smaller than the cementitious materials and water, air, etc. that are the components of the reaction. And this is called chemical shrinkage. However, as the paste gains strength, not all chemical shrinkage translates into physical shrinkage. And the physical manifestation of the chemical shrinkage is seen as autogenous shrinkage of the mortar or the concrete. So basically, as the paste gains strength, the shrinkage forces eventually are exceeded by the strength of the paste, and internal voids are created rather than the actual total manifestation of physical shrinkage. And as a result of shrinkage only occurring in the paste and the role of the aggregate skeletal structure, so the aggregate skeletal structure, which is quite different in RCC compared to conventional concrete, plays a role, and accordingly autogenous shrinkage of mortar is less than autogenous shrinkage of paste, which in turn is less than autogenous shrinkage of concrete. So if we look at this in terms of autogenous shrinkage of mortar and autogenous shrinkage of concrete, and then we look at the situation with fly ash rich concretes. So on the left hand side we see just mortar, and we see a situation with an OPC, which is the bottom line, where at 14 days you might get an autogenous shrinkage of mortar of the order of 410, 420 microstrain. When we effectively dilute that with 60% fly ash, that same situation, autogenous shrinkage in the mortar at 14 days reduces to something like 90, 95 microstrain. If we look at this then into concrete on the right-hand side, we have a situation where a 0% fly ash might give something like 85 microstrain of autogenous shrinkage at around about 550 days. Whereas that number is reduced to something under 10 microstrain when just 40% of fly ash is added. So again, autogenous shrinkage plays a critical role in stress relaxation creep. It's the origin, the key, or one of the two key origins in determining whether a concrete is susceptible to high levels of stress relaxation creep. And as you can see here, fly ash has a very, very significant role in reducing the autogenous shrinkage of not just a paste, but also a mortar and a concrete. So, as the process of hydration progresses, hydration heat increases the concrete temperature and the concrete attempts to expand. But thermal expansion is constrained, of that particular piece of concrete is constrained by what's happening in all of the concrete surrounding it, which is all experiencing the same effect. It's all trying to expand and pressing on the adjacent concrete. So constraint is created through that effect of each piece of concrete trying to expand and being constrained by the piece of concrete adjacent to it doing exactly the same thing, as well as structural constraint. So structural constraint will be foundation constraint. It will be related to the physical proportions of the concrete. So at the bottom of an arch gravity dam, where the width of the arch may be of the same similar proportions to the length of the arch, so you've got a square piece of concrete between abutments, the constraint there is going to be the physical structural constraint is going to be a lot higher than at the top of an arch dam, where you have a very thin long arch. So the arc length is long and the thickness of the structural section is very small. So it's a completely different structural constraint up at the top of the dam compared to at the base, particularly in the case of an arch gravity dam. So let's look more deeply into the mechanism that is stress relaxation creep. So as concrete is expanding due to increased temperature, but is constrained by material doing exactly the same thing surrounding it, that concrete experiences compression stress. Under this compression stress, the immature concrete experiences creep through which that compression stress is relieved or relaxed, and hence the name for this type of creep in stress relaxation creep. And one credible theory that has been advanced to understand what is happening in this process essentially considers the fact that the concrete under compression, the immature concrete under compression, experiences a situation where moisture is squeezed from the micropores in the paste into the macropores. So these macropores caused by chemical shrinkage and autogenous shrinkage. So the difference between the chemical shrinkage and the autogenous shrinkage, which takes the form of micropores being created within the paste. And as that paste then experiences compression, moisture from the micropores is squeezed into these voids that are the macropores, and in that process, the concrete structure, the paste within the concrete structure, collapses a little bit and relieves the compression stress that it's otherwise experiencing, and in the process shrinks. And now if we look at stress relaxation creep in relation to rotor-compacted concrete, in terms of the structure of the concrete, and particularly a higher workability RCC, the process of compaction under roller action really involves squeezing the aggregate skeletal structure together and releasing paste up to the surface. And this is very different and results in a very different skeletal structure to the concrete compared to conventional mass concrete. So one picture that I use to describe this difference is imagining conventional concrete as aggregate in a soup of paste, whereas RCC is a skeletal structure of aggregates with paste in between. And the very lower paste content and better developed aggregate skeletal structure that you get in roller compacted concrete through the action of roller compaction implies workable RCC is less susceptible than conventional mass concrete to autogenous shrinkage and early age stress relaxation creep. So from one side, because the problem that happens in autogenous shrinkage, etc., is in the paste, and because there is less paste in an RCC than is the case with most conventional mass concretes, there is less actual direct effect of the autogenous shrinkage, number one, and number two, because the skeletal structure is better established through roller compaction, the overall structure of RCC is less susceptible to the stress relaxation creep that would more easily occur in conventional mass concrete. All of these facts and these factors then result in quite a different situation during construction, relating to both low stress relaxation creep and the horizontal rather than vertical construction. So when placing low stress relaxation creep RCC for a dam and constructing horizontally, the thermomechanical behavior during the hydration process will be quite different to that assumed for vertically constructed concrete, conventional mass concrete. So if we look at the graphics here, we can imagine vertically placed mass concrete, which each block shrinks away from each other, implying that all of the construction load, the self-weight of each block is carried essentially vertically down into the foundation. Now, if we imagine that same situation where we've got contact or shear keys between those blocks, we'll have a situation where we're transferring vertical load from the higher blocks to the lower blocks through friction in the sides of each of those blocks. Now, if we think of a situation where not only do we not have the vertical blocks, we have a situation where these are not shrinking away from each other, but rather expanding with heat. As we're constructing, we are putting load onto a mass system. So it's nothing to do at this stage about taking load vertically down into the foundation, but we are creating a system with bridges within the mass itself, which will imply that the self-weight doesn't get down to the foundation in the same way as is assumed in two-dimensional concrete gravity dam design. So low stress relaxation creep implies that some thermal expansion occurs as the concrete temperature is raised during the hydration process. And as a consequence of continuous horizontal construction between the abutments, compression stresses are developed. So we apply a vertical load and we get bridging within that structure. Now let us look at the impact of the situation of low stress relaxation creep and start with specifically with arch dams. So due to the natural configuration of an arch or an arch gravity dam, the arches become longer and thinner in section with increasing elevation, and accordingly increasingly flexible with height. So the structure of a dam at its base, in terms of lateral stiffness, will be much stiffer than is the case right at the crest of the dam. Not only at the bottom is the length and width more similar, so we've got a squarer block, but we've got the restraint of the foundation. As we go further up the dam structure becomes longer and thinner, and remember, this action, any expansion will actually tend to push the dam upstream. So even the rigidity of the arch against load in a downstream direction is not applicable, because we're actually working with forces that will increase upstream movement. So the dam becomes much more flexible with height, and consequently expansion due to thermal temperature rise increases with height, causing the structure to lean progressively further upstream and resulting in the arches effectively and actually in reality being constructed progressively longer with increasing dam height. And this effect is equivalent to an extension of the arch at the crest level on structures of between 70 and 100 meters in height of the order of 50 to 70 microstrain, which implies that 50 to 70 microstrain of thermal shrinkage can actually happen in that arch crest before it effectively experiences any temperature drop load. So imagine the structure heated up and pushed back, and basically what will happen, ignoring the top of the dam, but as the bottom part, the mass of the dam, as that heat is lost, the dam will tend to lean itself further forward, closing any joint opening that has occurred due to temperature drop. So this is literally, it's like a pre-compression effect. We pull the dam upstream during construction so that it's got this pre-compression effect, which will mitigate the subsequent consequences of temperature drop load. And when we look at this effect specifically as in terms of temperature drop load, and again we plot our temperature time curve on the top there, and on the bottom we have a curve that reflects strain on the joint. And as we look at it, we can see, if we take where is the zero stress temperature, so this is the zero strain temperature, but it's effectively the same. So we have a situation, the dam goes into compression as the temperature is increased, and then as that temperature is lost, that compression is released. Now, as can be seen on these graphs from the Canalport Dam, the strain passes through zero at the point that the temperature T3 is pretty much the same as T1. So our T3 is equal to T1. And remember back to our earlier curves where in conventional concrete dam engineering, T3 is in fact equated to T2 rather than T1. And then again, bearing in mind that our stress relaxation creep is equal to T3 minus T1. So if T3 is equal to T1, that means that we have a situation of zero stress relaxation creep. And the final mass gradient structural temperature drop load will obviously then be substantially lower, essentially being T3 or T1 minus T4, rather than what would effectively have been in conventional concrete dam engineering, T2 minus T4. A very important structural difference in terms of temperature drop load on this dam type. Illustrating this point again, just for clarity, we have our graph T1, T2 and T4, and when we have a T3, that might be for conventional concrete, our T3 is either set at T2 or a degree or two below T2. So then our total temperature drop in a dam with outgrouted joints is large, being approximately T2 all the way down to T4. Now, if we're in a situation where our T3 is substantially lower, equivalent to T1, then as becomes very evident, the structural temperature drop, the long-term temperature drop load on the dam is much, much lower. And it's very relevant to make a statement in terms of understanding of how arch dams work. That in these situations, in the winter temperature loading, the displacements associated purely with temperature downstream from a cold winter are typically pretty equivalent to what the maximum displacements are related to the water load. So we can see that these effects are quite large. And with this reduction of the T3 value, it's very obvious that we're creating very strong opportunities for RCC arch dams whereby we do not need to grout joints. And that can involve, in the case of a temperate climate, it can mean very easily being able to construct without grouting, allow cooling to happen naturally, but filling the dam immediately on completion. In a more extreme climate, it may require dropping the T1 value, so pre-cooling the RCC to bring that temperature down to an acceptable point, such that the temperature drop load is not is still manageable. Now moving on to what this means on gravity dams. So great opportunities in terms of arch dams, but negative effects in terms of gravity dam, because low stress relaxation creep can imply that gravity dams do not necessarily act as two-dimensional structures. And structural bridging must be carefully assessed, particularly in high dams in narrow valleys, or where zones of weak material are present in the foundation, because literally we create a bridge across those zones and we don't have a contact pressure between the dam and that foundation potentially in these places. That contact pressure can be less than the hydraulic pressure, and if we have an erodible material on a contact, this can obviously result in a very serious erosion beneath the dam. And consequently, analysis requires very careful structural evaluation of the dam structure under gravity and thermal loading. So our thermomechanical analysis must be very carefully consider the process of construction and subsequent loading. And without a bench foundation on a steep abutment with a lower strength rock mass, the extremes of the dam may slide down as the hydration heat is dissipated. And this is particularly the case. What would normally happen in a gravity dam, each of the blocks would carry their own load vertically and they will shrink away from each other. But because of the thermal expansion that we have in low stress relaxation creep, we actually create a situation where we lift our dam. So the top piece that we're putting on is sort of stretched over this top of this lifted area. And as that lifted area cools and shrinks back down, it will pull the sides of the dam down the abutments. So those flanks of the dam must be designed to be stable on their own abutment. So where you have a weak abutment, a steep but weak abutment, you have to look very carefully at the design of the joints to make sure that there isn't a traction pulling the concrete downwards, and or that each block is stable on its own and doesn't develop a downward shear action and will be allowed to open such that you'll have quite large opening on the joints on the upper abutment. Additionally, high levels on a lower deformation modulus foundation, higher levels of horizontal tension will develop along the dam base. It's very similar to a rigid beam on a flexible foundation, that concept. And it can be necessary to bench the foundations and provide distinct joint systems to ensure debonding of all of these joints. Not so much in the central and the lower section of the dam, but in the upper abutments. And this must be looked at very carefully in even the design of gravity dams. Now, raising all these issues about stress relaxation creep and thermal and thermomechanical analysis, we need to really talk about what is the correct approach for stress relaxation creep and thermomechanical analysis. And stress relaxation creep relieves the containment compression stress caused by restrained thermal expansion early during the hydration process. And creep can only occur once the hydration process creates micropores and macropores in the gel to allow the migration of moisture. Until that point, it basically it's like compressing a fluid. But thereafter, creep will only occur until the compression strength of the concrete sufficiently exceeds the containment compression force. So in the same way as autogenous shrinkage is a lesser form of chemical shrinkage, which stops chemical shrinkage once the paste has sufficient strength, a similar effect will occur in the compression or the stress relaxation creep in concrete. So once the concrete has gained sufficient strength, it will be able to resist those compressive forces and the creep will not continue. So at the beginning of the hydration process, the RCC will act more like a contained liquid, and only as the hydration gel shrinkage occurs, simultaneously with thermal expansion, will the susceptibility to stress relaxation creep start to develop. And stress relaxation creep will develop during the first few days after placement. So this is probably something that happens between day 1 and day 4, obviously depending on the particular mix, etc. But it's occurring in this very early period. And determining the temperature rise on the 4th day throughout an entire dam structure and establishing the associated compression stresses at that time in those particular points throughout a dam would be a very complicated and complex exercise. And for a typical fly ash RCC, the temperature rise at day 4 has been demonstrated to be consistently plus minus 65% of the maximum hydration temperature rise, whether that be adiabatic or whether it be conditions due to some exposure of the surface. So in view of the fact that establishing temperatures at day 4 across the entire dam structure is very difficult, it's much easier to establish the maximum temperature, so the maximum temperature at the peak of hydration, the T2 temperature. Additionally, stress relaxation creep, the function of stress relaxation creep should realistically be based on the elastic modulus as applicable during the time the stress relaxation creep develops. But this is again a very, very difficult, or not necessarily realistic thing to be determined or modeled. And however, using a stress relaxation creep function that's based on T2, or in fact the temperature rise, the T2 minus T1, and the mature elastic modulus of the RCC, a realistic stress relaxation creep curve was developed to produce a realistic response within a three-dimensional arch structure. And this demonstrated the nature of the type of stress relaxation creep function that was applicable. Basically working with a prototype structure where we understood the response in the different parts of the structure. So we were able to back analyze what this would look like on the basis of just using the T2, the maximum temperature, and the mature elastic modulus. So this isn't an absolute curve that defines when this happens, this is the response. It's an approximation that allows us to use the simplified information of T2 and mature elastic modulus. And the stress relaxation creep curve must be used basically then to reduce the compression stress in an iterative manner until a balanced situation of compression stress and stress relaxation creep is established. So at the T2 temperature, which is not a state of time, it's a state of temperature. So throughout the whole structure, we look at what are the the containment compression stresses throughout the structure. We look at them, we plot them onto this curve of compression stress against stress relaxation creep. We pick off a value, we put this back into the analysis system at every single node of the structure, and we iterate it again, because once the stress relaxation creep has gone into the model, it reduces the compression stress and therefore picks itself a lower value of stress relaxation creep. So we have to iterate this a couple of times to get to a point where we've got a balance between the applicable compression stresses and the stress relaxation creep. But through this iteration, we end up with a full picture of the stress relaxation creep distribution node by node throughout the three-dimensional dam structure. And very typically, we'll see a picture where we have higher levels of stress relaxation creep in the lower parts of the dam structure, reducing with height, again through not simply related to the dimensions or the temperature rise of the structure, but significantly related to the level of flexibility of the structure higher up. And this gives us then a situation, we have a distribution of stress and strain at the critical point in time, and from that loading we can then look at, or from then that condition, we can then derive what are the stresses and strains in the structure at any subsequent point forward until full dissipation of the hydration heat at the T4 conditions. So while earlier thermomechanical analysis didn't understand and could not quantify the real mechanisms behind that were occurring, the real stress relaxation creep mechanism, it's of interest to review the typical spacings selected for induced contraction joint over history with conventional dams. And in this regard, a graphical presentation published recently of Chinese experience is very telling. So in the early days of RCC dam construction, there was a school of thought that believed that induced contraction joints could virtually be eliminated in RCC dams due to the low hydration heat rise. But practical application has demonstrated that a joint spacing of between 20 and 35 meters is realistically optimal. These aren't, the induced joints aren't expensive, it's a question of balancing what is needed, what is sensible, and what is practical in a real situation. And while this number 20 to 35 meters will depend on the climatic conditions, the dam height, and the founding conditions, it's very interesting to note that this is something that now is sort of being accepted across all RCC dams, even though the actual theory behind it is not proven. It is more about practical experience that's demonstrated this to be the right answer. So now let's move on to look at the important differences between roller compacted concrete and conventional mass concrete dam design. So for gravity structures, the design of an RCC dam has generally followed the same approach as is applicable and was developed for conventional mass concrete dams. But realistically, there are two significant differences between RCC and conventional mass concrete that must be considered in the process of design. Both of these effects are related to horizontal rather than vertical construction, And the first difference relates to low stress relaxation creep in combination with horizontal construction. If we consider that our contraction joints, our induced joints in RCC dams, that are not formed but induced and typically aligned with a tolerance of plus minus 50 millimeters. And that 50 millimeters is not realistically an upper level of tolerance. It's a practical reality that we probably are constructing with a realistic deviation of 50 millimeters one side and 50 millimeters the other side. And this implies that we have vertical and horizontal alignment of our induced joints that varies by 100 millimeters, effectively creating vertical and horizontal shear keys in our RCC. And if we look at Indian Standard 6512, which is the criteria for design of solid gravity dams, this states that when adjacent cantilevers are of differing height, load will be transferred laterally and by shear between blocks unless the contraction joints are neither keyed nor grouted. And as discussed under section 5 of this presentation, this situation implies that some measure of three-dimensional structural interaction must always be considered in the design of RCC dams. We are creating these shear keys, and in a situation of low stress relaxation creep, we have joints that don't open very much. So we have shear keys that will transfer load between adjacent blocks. And this may not be relevant on a long level gravity dam of similar section, but certainly is on a site where the abutments are steep and the crest length is not excessive. So we have to consider now three-dimensional issues in our gravity dams in the case of RCC. As I said, it may be possible to dispel them as not significant, but they must at least be considered. The second difference between RCC and conventional mass concrete is the need for simplicity in RCC dam design. Simplicity in form to allow simplicity and consequently speed of construction. It's extremely important to understand the difference between the requirements and limitations of horizontally constructed RCC and vertically constructed conventional mass concrete. And these two figures illustrate this significant difference. In the case of RCC on the left, what you need is a large open area to allow very simple, very rapid transportation, dumping, spreading, and compaction, or horizontal compaction of your RCC layers. Anything that goes inside that will cause an interference. Now, if we look on the right side, we see a conventional concrete construction, and in the middle blocks, you can see that there are outlet pipes being added. And those outlet pipes, yes, they slow the construction down in that particular block locally, but with the adjacent blocks being able to continue at full speed unaffected. And once the pipes are installed and finished, those central blocks can be quickly brought up to be of a similar level to the all adjacent blocks. So the inclusion of items or pipework, etc., through the dam in the case of conventional concrete doesn't have much real effect on the achievable construction pace. That is not the case in an RCC dam. It's quite the opposite. So as soon as you put anything in the middle or anywhere in the structure and you're constructing horizontally, that will interfere with your placement process, and consequently anything that does get included there has to be very rapidly nowhere is an understanding of this requirement more important than in the design of inlet-outlet works. Get it wrong and you can easily get a situation where the tail wags the dog. And This slide provides that a very strong indication. The RCC on this particular dam took twice as long as it should have, because the entire construction was determined by the design of the inlet outlet works. Clearly the wrong thing to do for an RCC dam. This is a misunderstanding of the requirements of the design of an RCC dam. Get it right, however, and it's very easy to accommodate inlet outlet works in an RCC dam, with the primary principle being that whatever is included, it doesn't affect the RCC placement. So the RCC placement simply continues up and over and above whatever is taken through the structure. So but it is essential to recognize that in the design. And as an example, just rationing the design of the outlet works at the Springgrove Dam in South Africa reduced the entire dam construction program from 28 to 19 months. So it wasn't changing the function of the inlet outlet works, it was just rationalizing the arrangement, applying the thinking that the construction must be designed in tandem with the RCC arrangements. That was basically possible to reduce the construction program of the dam by approximately 1/3. And we're talking 1/3, and that's the sort of thing that can actually have an economic effect on the project. So it's not just about a lower cost construction, it's about bringing the project online sooner and having an economic benefit, a return on capital sooner. It's an extremely important principle. So spillways can also slow RCC dam construction. And where you have a very simple traditional stepped spillway on an RCC dam with energy dissipation on the steps and in some sort of apron or other at the bottom, has very little effect on the placement. But when you're looking at a system of higher capacity, where you can't dissipate over the steps, higher concentration of flow, or when you're dissipating energy at the crest. In these two cases, you can quite easily get into a situation where it significantly slows down the construction. And that may not be a problem in cases where you've got a dam that's going to take 1.5 years to fill, for example. But at the Changuinola 1 dam, which was filled from empty to full in 33 days, obviously it was very significant to ensure that the spillway was available immediately on completion of the structure. And consequently, the construction of the spillway was designed to lag the RCC placement by just 2 weeks. And consequently, there was no restriction. The spillway had no impact. But in other situations, it's quite easy to make that mistake and slow the date of impoundment down by the type of construction used for the spillway. The impact related to spillways is much higher on an RCC dam than is the case on a conventional concrete dam. So all inclusions in RCC incur an impact on the achievable RCC placement rates. And slope galleries can be particularly problematic. And I could talk to you for probably at least half an hour on what you see in these pictures, but suffice to say that never mind the design problems that are associated with this situation, it is a problem in terms of construction scheduling, and it's substantially better to use systems of horizontal galleries and vertical shafts. Obviously, these need to be looked at very carefully to make sure operational conditions are still okay. The impact on uplift need not be at all significant, but from a construction point of view, this type of system is substantially better. And while a precast inverted U gallery form may not be the cheapest on paper, in terms of its benefits in construction speed, it is definitely the best system to use on an RCC dam. Okay, so let's look at the differing RCC requirements for differing RCC dam types. And we spoke about this initially earlier in the presentation. RCC mixes will be discussed in detail under a separate presentation. So I'm not going to go into the details of RCC mixes or how the design thereof works, but it was considered worthwhile to emphasize the respective influence of these different mixes and the related requirements in relation to dam design. In earlier RCC development, there was talk of the geotechnical and the concrete approaches to RCC mix design. And that was not received well by certain people, but from my perspective, it's quite a useful way to think, and it's a useful way to create a differentiation in thinking of how these concretes actually, in their hardened states, how they actually work. And in its hardened mass form, an RCC will act as something between a stabilized fill in the sort of the geotechnical point of view, all the way to an absolute solid monolithic concrete. So these options exist from one all the way to the other in RCC. We're not restricted. There isn't one solution. There's not one just weaker or stronger type of concrete. We have a completely different system of concrete with, as I say, at the lower cementitious end, something more like a stabilized fill where we have heterogeneous layer profiles and all this sort of thing, all the way to a very, very homogeneous and solid concrete where you cannot really differentiate any weaknesses between layers and that, etc. At the lower end of the cementitious scale, core drilling is notoriously difficult and simply cannot successfully produce meaningful cores for testing before an extended age. So you cannot design a concrete with very low cementitious materials, drill within a couple of weeks and expect to see what the strength, what the shear strengths of that concrete will be. And related situations have recently resulted in the particular dam being actually considered unsafe. And in this context, it's extremely important to ensure that the design of each RCC dam is based on the actual nature of the constituent hardened RCC, which is determined not only by the mix design, but also the methods of construction that are applied. So while hard fill construction may be very rapid and efficient, it's not appropriate to design a dam as an RCC gravity dam and to build that dam as a hard fill dam. And this has happened many times in RCC. There are many RCC dams that have been designed as gravity dams, but not really constructed with good enough materials for them to be gravity dams, more at the end of what would realistically be called hard fill. So moving along to look at different facing systems for RCC. So it's not really realistically possible to create an acceptable finish by roller compacting concrete against formwork on its own. And so different facing systems are available. And these include reinforced concrete or precast concrete panels, extruded concrete curbs, two forms of grout-enriched RCC, which I'll describe in detail, GERCC and GEVR, and then we have IVRCC, which is internally vibratable RCC. So this is RCC that can either be compacted with a vibratory roller or by immersion vibration. Conventional mass concrete. Conventional mass concrete is often used as a surfacing to RCC, and there will be somewhere in all dam structures where conventional mass concrete and RCC are interface at some point. And often the compaction at the interface between conventional mass concrete and RCC is poor, and consequently low strength and permeable material exists. Theoretically, a good bond between conventional concrete and RCC can be achieved when both RCC and CBC are compacted simultaneously. However, the reality is that this is very difficult to do, and it's an ambitious objective to actually achieve that. It interferes with construction quite considerably to have to actually do that. Then we have reinforced and precast concrete panels, but it will never be possible to effectively bond reinforced concrete or precast concrete to roller compacted concrete, and hence it's usually necessary to treat that particular element as a separate skin, and often there will be a GE RCC or a grout enriched between the RCC and that precast element. The reinforced concrete or precast panel will also usually be constructed before the RCC, which in terms results in an inefficiency of the one before the other. Extruded concrete curbs. So this is was quite frequently used in early RCC, and however the extruded curves must be constructed before the RCC, and they're therefore on the critical path, and they can only be realistically used for downstream faces because they can't be used to create impermeability. Similarly, there will be no real bond between this medium and the roller compacted concrete adjacent to it. Then we have grout enriched RCC, so this is GE RCC, and this involves putting grout into RCC from above, from the top of the surface layer. And when developed, GE RCC represented the simplest and most effective and most technically appropriate method for forming the external face of an RCC dam. And when with GRCC, the operation of creating the skin is not on the critical path, which allows increased placement tempo and while still producing a very good surface finish. And with the right application in modern experience and development has shown that the right application can make GERCC very effective, giving very continuous cores with no bonding issues between layers. The only problem with this type of enrichment is the necessity for a relatively high water-cement ratio to allow the grout to penetrate from above and therefore be flowable. Then we have GEVR, which is again a grout-enriched vibrated RCC, but the grout is placed at the bottom of the layer rather than the top of the layer. And this works better than GE RCC for high-paced RCC. It also has a better certainty of grout penetration, because whereas putting the grout on the top of the layer and vibrating, you can't see what's happening at the bottom of that interface of that layer and the previous layer. Whereas with GEVR, you are vibrating the grout up through the RCC. So when you see it on the top surface, you know it has penetrated through the entire depth of the layer. You can use thicker grout, a 0.6 to 1 water cement ratio is quite easy, which means that you can have higher strength and greater durability of concrete on the surface of the dam, which can be very relevant in particular instances. Negative side is that there is an additional activity on the critical path. It's necessary to make these ponds of grout ahead of the bulldozed RCC, and therefore there's additional preparation. When the RCC being used is actually too workable and has too high a paste content, grout can actually rise up against particular inserts into the RCCs, such as water stops, such as the formwork, and this can result in a thin grout being creating a film against certain entities, which can then shrink and crack and can increase permeability. And it's just a question of only using the grout or even the quantity of grout, establishing the quantity of grout on the basis of what the particular RCC requires, not designing it for a particular number or volume of grout. Then we have IV RCC, which is the simplest system for forming the external face of an RCC dam. All activities involved are off the critical path. It creates good bond between the body of the RCC and the surface. It gives a good surface finish, but it requires a higher paste content and or high workability aggregates, and so its use is realistically limited to super retarded and high workability, higher cementitious RCC. On the downside, compaction can sometimes be hard work, and in which case it can actually be easier to add grout using GVR and to increase overall construction efficiency. I'm now going to talk briefly about RCC arch dams, and not in any real depth related to the design. But there are 83 RCC arch dams in the world, 71 of which are thin arches and 12 of which are thick arches and arch gravity structures. And the highest of these is the thin arch Wanjiakuzi Dam in China, which is 168 meters high. Almost 30% of all RCC dams in China are arch dams. And there are essentially two types of RCC arch dam. Those constructed in China or by Chinese contractors using the Chinese technology, and those constructed elsewhere. And the two types are very distinctly different. Modern Chinese technology RCC arch dams are essentially conventional concrete arch dams constructed in RCC. On the other hand, non-Chinese technology RCC arch dams are RCC dams designed to make use of three-dimensional structural function. It's quite a different concept. Very briefly looking at the Chinese arch technology, which has involved joint systems to allow additional displacement, and what is called formed and induced joint systems within the RCC itself, which are actually rigid systems that are installed before RCC spreading, which has a huge implication in all sorts of ways, and particularly in terms of achievable construction speed. Grouting is either undertaken in stages with multiple systems or re-injectable systems. To look very briefly at other systems that have been installed at Changuinola 1, Kotanli, Kurulu, and partly at Jani Dam. And these have involved an induced system where a re-injectable grouting system has been included in certain places strategically where required, but with a modern trend away from this, the requirement to grout at all. On the other hand, in more extreme climates, systems have been used where part of the dam has been pre-cooled, and to take advantage of the low stress relaxation creep effects that I've been talking about earlier. And this has meant that some limited pre-cooling and grouting has then allowed the structure to subsequently tighten itself over time. So usually what happens with a dam is, arch dam, is it's grouted and it may need re-grouting as it loses some of its temperature. In fact, what has been done on these dams is that they've been grouted in a manner which allows the structure to tighten further during subsequent cooling, which has been very beneficial. So reviewing the concrete placement rates achieved for arch dams, RCC arch dams, on the basis of Malcolm Dunstan's curve of average monthly rates of placement against total RCC volume, it's interesting to note that the fastest rate achieved in Chinese technology is 28,000 cubic meters per month, which is very substantially slower than applicable for a similarly sized RCC gravity dam, and it's even slow compared to what might be expected for a similarly sized conventional mass concrete arch dam. On the other hand, it can be seen that the achievable average RCC rate for non-Chinese technology arch dams is similar to that to RCC gravity dams, with Changuinola 1 at the top end of the envelope, despite the fact that it was at the time at least, the most rain impacted RCC dam construction to that time. So Chinese technology is more complex, slower, and generally requires post-cooling and more complex spillways, but will gain the benefit of between 5 and 20% less RCC than a conventional arch gravity RCC configuration. Non-Chinese technology has required, by the same token, between 5 and 20% more RCC, but can be constructed at normal high RCC placement rates and can impound immediately on completion without the need for post-cooling and grouting. Non-Chinese RCC arches do not need to adopt a traditional arch gravity form, but tend to be configured for maximum constructional simplicity and speed. So in summary, in relation to RCC arch dam, it's interesting that almost 30% of all RCC dams in China are arches, while less than 2% of RCC dams elsewhere are arches. Certainly, China has many arch sites, but there seems to be a general reluctance to use this arch technology, RCC arch technology, elsewhere in the rest of the world. And it has only recently been the case that these dam types are starting to gain popularity. So while RCC will generally be the optimal solution for a gravity dam, assuming it's designed for simplicity, a much less easily defined line exists between RCC and conventional concrete arch dams. So where the line exists, where vertical construction has a benefit over horizontal construction. And vertical construction becomes more efficient than horizontal construction on narrow dam sites with steep abutments for several reasons. Consequently, the most obvious place for RCC arch dams is on relatively wider sites, such as suit thicker arches or arch gravity configurations. And although there is certainly no need to restrict the structural configurations of arch gravity dams to vertical and constant inclination faces. To gain the benefits typically associated with RCC for an RCC arch, simplicity remains the key element and the key requirement. And the opportunity in RCC arches, particularly taking advantage of low stress relaxation creep, are very significant. So let's look briefly at the primary success factors in RCC dam design. So as a sort of a pre-summary. So the success of an RCC dam is usually measured in the efficiency of its construction as well as its water tightness in operation. This success cannot, however, be achieved without the correct approach at the design stage. And efficient RCC dam construction is as much the dam designer's job as it is the contractor's job. The planning necessary to assure peak RCC efficiency during construction goes right back to the project feasibility stage and requires the involvement of RCC engineers who understand all of the requirements. It's perhaps due to its perceived simplicity that RCC dam construction so often goes so wrong, and possibly as few as 10% of all RCC dams completed to date have realistically benefited from the real potential of roller compaction. So, in summary, the presentation demonstrates the broad range of gravity and arched dam types that can be designed for construction using RCC. It further touches on the different RCC types associated with these different structure types, illustrating the range of RCC characteristics from a geotechnical material to a quality concrete that implies very different dam configurations, designs, and construction approaches, which related limitations are not always so well understood or respected. A particular emphasis is made on the critical importance of good design for RCC dams, highlighting the fact that there are more things to take into account in the case of the design of an RCC dam than is the case for a conventional mass concrete dam. RCC is a medium with great flexibility, but for which good knowledge is required in order to take advantage of what each RCC type can offer. Stress relaxation creep is a key issue for RCC dams, with low stress relaxation creep RCC presenting opportunities for very efficient arch dams, but complicating the design and behavior of RCC gravity dams in steep valleys or on variable founding conditions. Understanding the mechanisms of our stress relaxation creep and its variability for different RCC types, an additional parameter must now be considered in the design of all RCC dams. And this parameter must be correctly addressed and modelled in all thermomechanical analyses for RCC dams. The differences in RCC related to horizontal construction must be given full consideration in dam design. And the key element is maintaining simplicity in design to ensure simplicity and consequently speed of construction. It is substantially more difficult to successfully include inclusions within an RCC dam than is the case for a conventional mass concrete dam. Inlet outlet works need to be specifically designed for RCC construction, and careful thought and planning is required for spillway, galleries, and all other inclusions. When you get it right, RCC dams and RCC dam construction are simple and straightforward. But it's perhaps due to its perceived simplicity that RCC dam construction so often goes so wrong, with probably less than 10% of all RCC dams having benefited from the real potential of this technology. An RCC dam will never be successful in construction unless consideration of construction is given the necessary attention in design. Simple RCC arch dams taking advantage of low stress relaxation creep and the consequential RCC pre-compression offer significant opportunity for efficient three-dimensional structures without the need to post-cool and grout joints before impoundment. I thank you for your attention, and I'm happy to answer questions.
Thank you. Thank you, Dr. Quentin Shaw, for making an excellent presentation and detailed presentation on RCC dam design. May we proceed further for the question answer session? May I request to the participant for their questions, please?
I have one question.
Please, sir.
The values shown for shear strength and tensile strength in the presentation, whether they are laboratory values or measured in field.
Thank you for the question. In fact, those are very much indicative numbers. If you refer to Bulletin 177, you'll see that basically those numbers, they are guide numbers. In Tim Dolan's presentation on RCC dam performance, you'll see a little bit more information on actual data that's come out from testing. But these numbers are just guide numbers to differentiate between the basic general properties in design. And in each design, it will be different. It's not just dependent purely on cementitious materials content. It's dependent on the nature of the materials, the aggregates as well. So one thing that is very, very, very important and has been demonstrated recently is that we have to do testing to verify the properties that are used in design. So in our preliminary design phases, we can use these sorts of numbers, but we must be very careful on what we then, how we verify that. And that is a huge part of what is done in the full-scale trial. So your full-scale trial realistically must be drilled, and the properties between layers in the various different forms of hot, warm and cold joint treatment need to be tested to verify that the properties that have been used in design have been achieved. So those are guide figures, but there's a big emphasis in the industry in having to verify those numbers for final actual implementation design. And this is particularly important when we are using lower factors of safety, as is commonly the practice currently, very different to the sort of practice of 30 years ago when the higher factors of safety were used and a greater assumption could be made on the basis of properties on joints, etc. Thank you. I hope that answered the question.
Thank you.
Mr. Anil Jan has raised the hand.
Yeah.
Would you like?
Yes. Sir, in your initial presentation, initial slides, you have shown a curve showing T1, T2, T3, if you remember. So those values of temperature, I think, and for T2 it is about 100 degrees centigrade. So are these typical values or just representative values? Means in a RCC dam, can I expect a T2 value of around 100 degrees centigrade? Even
No,
for the...
well, if it said 100, sorry, yes. So if it said 100, that would be 100 degrees Fahrenheit.
Okay, then it's
yes,
all right.
yes. So, you know, typically it obviously all depends on your placement temperature and your hydration heat. Yeah, I mean, again, rules of thumbs for concrete is an absolute maximum of sort of 50, 60 degrees centigrade. But realistically, you'd want to keep that preferably more in the 30s or maximum in the 40s, depending on the environment, of course, and depending on the final equilibrium temperatures.
Yeah.
That 100 was Fahrenheit.
Yeah. One more thing. In the slide where you mentioned about impact of low stress relaxation creep in gravity dams on abutment, where you have shown in for unbanked abutments, there is a possibility of developing sliding down of the concrete and creating that. But in India, mostly in almost in every condition, we have banked abutments. So what is your opinion in that condition, whether that effect will be there or not? And one more question. And what, in your opinion, what could be the maximum compressive stress due to SRC in gravity RCC dam of 100-meter high?
Okay, thank you for the question. So in relation to the first question, benching of abutments on a gravity dam can be dangerous. So it's a very different situation for a conventional mass concrete gravity dam, which undoubtedly you need to bench the foundation for stability of each individual block. In RCC, it's quite different because of this horizontal construction. So if you bench the foundation and you've got to then be very, very careful with how you arrange and induce your induced joints. Otherwise, you can end up with diagonal cracking coming off those.
Okay. Sorry, it got stuck.
Okay, we're back. Yes, sorry, I don't know what happened there. Apologies. So very, very importantly, so it's the same principle as a culvert in a trenched foundation or a culvert sticking out of the surface. You'll get those effects because of horizontal construction of an RCC dam. So if you use bench foundation, you really need to look very carefully at what's happening in terms of those stresses in the structure during construction and how your joints will separate, because if they don't separate, you could end up with a diagonal crack that goes away from your joints, and that has happened on several occasions. And in the case where where we had to do a bench foundation, we had a very weak foundation. So we had 1.4 gigapascal elastic modulus or deformation modulus on a foundation on a dam of 90 meters height. And there, what we did was we made very, very distinctly certain that our blocks could separate from each other and not hang up. So they could separate and pull away, so that each block would then be stable on the bench foundation. So we made specific arrangements to make that benching work with the structure, and it's a very important factor to consider. So if you're going to whichever approach, you need to understand what will be the consequences, and it is now part of the design thinking that must be applied for RCC dams, which wasn't really the case previously. And to answer your second question, the sort of numbers that you're looking at is in terms of compression stresses. So if you have it's one thing about the height, but it's more about the bank-to-bank direction, because it's how flexible is that structure. Any dam, any gravity dam, will tend to have its maximum load on the upstream side, and it will tend to tilt over up towards the upstream. Immediately that happens, you're creating some further flexibility higher up the dam, and your compression will then increase that push upstream. On an arch, you've got that flexibility, so a lot of that effect is dissipated into actual physical expansion. But basically, you can look at sort of quite commonly 2 MPa compressions, and pushing up to 3 and maybe 4 at the absolute maximum, depending on the thermal expansion or coefficient of the concrete and the temperature rise, plus the constraint created by the physical constraint of the foundation and the applicable flexibility of the concrete at that point in terms of width of the width of the valley and the length of the dam in upstream downstream direction. And what you see happening during the placement, if you have strain gauges orientated left bank, right bank, and if you have them orientated upstream, downstream, you see a completely different effect. So the left bank, right bank will go into compression, and the upstream, downstream will actually show expansion. So you're getting a secondary effect of relief of some of that compression in an upstream, downstream movement. Okay, so that also dissipates some of the compression stress. It's quite complicated.
Thank you.
Thank you.
May we have the next question from Mr. Vivek Tripathi, please?
Yeah, my question is in RCC gravity dams, how do you provide form drains?
Can you repeat the question, please? In RCC gravity dams, how do you provide the?
How would you provide form drains for collection of seepage?
Oh, formed drains.
Yeah.
Yes. So with so in 2 ways. So where you have a drain on the water stops, so you will tend to have a series of water stops with a drain in between. Okay, and the number of water stops may vary depending on the height of the dam, but you will have a formed drain in between. So that is placed and cast in the GERCC or the GEVR or the skin. So that's quite easy. But the drain in between, for example, in between the galleries. So if you're draining the dam itself, it's quite common to have 75 millimeter holes at 3 meter centers across the entire structure, so acting as a drain into the galleries. So those you would drill. So you drill from gallery to gallery, and that's usually why you would put your galleries within an absolute maximum of 40 meters separation in order to get the accuracy of the drill to hit the gallery beneath. So 30 to 40 meters is realistically the maximum distance between galleries, and you drill between galleries to create that system to capture seepage that has got past sort of the nominally impermeable part of the RCC. It's definitely not a good idea to put any form of solid form up through RCC. It again just simply interferes with the placement too much.
Because in gravity dam, we generally provide 3 meter center to center all these form drains. If we are providing during construction by putting drains in GVER, it will hamper the speed of construction. So whether 40 meter drilling will be accurate with this spacing always?
Well, so you need to be very careful with your driller, and if you can't do that, the accuracy on 40 meters, then you need to look at galleries closer together, more like 30. But there are several strong reasons. So you'd never put, if you've got drains in the GERCC in the surface, those are just between the water stops. Those are just to catch water that has seeped past the water stop system and to route it to the gallery. That's their only purpose. They're not general drainage for the dam structure. And if you put those drains, for example, in a line, formed drains at say about 8, 9, 10 meters downstream of the upstream face, for example, if you put them, you are creating a structural weakness in your dam, because the dam must be built on either side of those drains. That's a fatal, not a fatal flaw, but it is exactly the sort of thing that you don't do in RCC. So you can come back and you can drill from gallery to gallery because it's not on the critical path. When you put those drains in, it doesn't really matter time-wise. It's not a critical path activity, but trying to form them inside the dam is, and that will probably have an impact on your construction speed of the order of 50%, maybe 30%, something like that. It will have a big impact, and you are then in a situation where you've got to do RCC on one side of them and RCC on the other side of them. So you're actually creating a physical weakness as well. Definitely not an advisable thing to do.
Any further questions?
Yes, ma'am.
Yeah, please.
So I wanted to ask whether the deformations due to SRC, the stress relaxation creep, and other thermal effects, what is the effect of these deformations on the facing, let's say GEVR? Do they have any effect?
No, none at all. They undoubtedly have an effect on the surface of the joint, the way that the joints open, surface zones, yes. But in terms of the facing systems, GERCC, IVRCC, GVAR, not at all. You don't see any impact on that at all. If you use a fly ash rich RCC in those forms, you very good quality finish that doesn't crack for drying shrinkage and doesn't really see any crack forms. But you don't, the actual relaxation creep issues, you don't see any impact on the surface. There's no surface falling. You see, the surface, you have to remember, never really experience the peak of the hydration temperature. Yes. Internal zones do. So you never get a situation where you'll get on the surface because of compression. At least it hasn't been seen yet. But you know, you do certainly on an arch dam when we were measuring that expansion on the upstream side, canola, we were in increasing compression on the downstream side. But because the nature of the way joints open, it still had a slight opening at the actual surface, so there was never any contact on that surface.
Okay. Thank you, sir. Thank you.
May I ask one question?
Yeah, please.
Thank you.
It is just again related to number. Can you just suggest me how much tensile strength of GEV RCC increases as compared to normal RCC?
Well, GLCC, the issue with GRCC is the fact that you're adding
More grout
with a water cement ratio of the order of grout. You're adding grout with a water cement ratio of the order of 0.9. So theoretically, you're actually diluting the strength of the RCC on the surface. And what's been found is that doesn't seem to really be the case. You tend to get very similar strength in your GRCC, sometimes slightly, but not.
Sorry, I couldn't follow due to
itself.
Sorry, I couldn't follow. Sorry, I couldn't follow you due to disturbance in, I think.
I'll repeat. So yeah. So let's say you have an RCC with a water cement ratio of something like 0.65 or 0.7, and then you put a water cement ratio of 0.9. So you're actually in total you've got a lower water cement, a higher water cement ratio in the GRCC than in the RCC. In GVR, you'll have a similar water cement ratio, if not higher, in the surface than in the main body. But when you use GRCC, you've got slightly lower, a higher water cement ratio in the actual concrete that's being vibrated by a motion vibrator. Despite that fact, there are some that's slightly lower, but it's not significantly lower than the RCC. Then basically you're compacting it as a conventional concrete. So by the fact that you're compacting as a conventional concrete, you can, assuming that your construction methodology is solid and correct, you can end up with higher as a conventional concrete as opposed to a roller compacted concrete. Roller compaction has an effect as the one layer is placed onto the other. There's a movement, there's compaction down, there's orientation of aggregates into tend to be left bank, right bank sort of thing. So you get in RCC, you get a higher horizontal tensile strength, vertical tensile strength. The immersion vibrated concrete, that won't be the case. So there is some advantage of in that respect. But like I say, the problem is you've got a higher water cement ratio, so you sort of lose some of that benefit. But realistically, whether GRCC, whether GEVR, whether IVRCC, these are skins that are thin and will not really, they're not thick enough to be used structurally. As a difference to the RCC itself.
Usually of the order of 0.5 meter or so.
Yeah.
Thank you.
Thank you.
Now I request if the participants still have more questions, they may write to us, to the organizer CBIB. We will arrange the respective answers from the respective resource speaker and get back to you over the email. Thank you. Thank you to the participant for such an interactive question answer session. I would like to convey my special thanks to Dr. Quentin Shaw for sparing his valuable time for conducting today's virtual session. I'm sure all the participants must have benefited from his vast knowledge shared during the program. See you all tomorrow for day 2 session at 1100 hours IST. Thank you. Thank you all. Stay safe, stay healthy. Thank you.
Thank you very much.
Thank you very much.
Thank you.